Good morning, students. Good morning, sir. Once again, welcome back.
Good morning, sir.
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 Good morning, everyone.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Sir, control is yours, sir.
Okay, sir. Thank you. Yeah, dear students, are you able to see my screen? Hello.
Yes, sir.
Yes, sir.
Yeah, am I audible? Is my voice clear?
Yes, sir.
Okay.
Sir, but the volume is little bit low. Sir.
Okay, volume I'll increase. Huh? Yeah, now is it audible?
Yes, sir.
Hello. Yeah. So we're about to commence the power system course. I hope all of you are electrical engineers. You might be in your final year or you might have completed your graduation. So just to say a few about me, I'm Muhammad Rafi, working as a superintendent electrical in ONGC Limited. And I passed out from IIT Kharagpur in 2008. I did masters there, and I have been teaching for GATE for the past 10 years. This is about me. And yeah. A few students, let us admit them. Yes. Now, basically, what is a power system? So any one of the participants can give their view about what is a power system. Yes, someone can unmute and speak. Hello. Are you able to see my screen? Hello.
Yes, sir. Able
sir.
to see.
Yeah. Are you able to listen my voice?
Yes, sir.
Yes, sir.
Yeah. Good. Wonderful. So in power system, basically what we're trying to do is, it's a largest man-made network. Power system is a largest man-made network which consists of generation, transmission, distribution of electrical energy. So we require energy for our day-to-day living. We require energy to tell me a few basic things which everyone requires energy for. You require energy to drive your vehicles that you're consuming in the form of hydrocarbon, where you buy petrol, diesel, or you propel your vehicles. Okay. You require vehicles for your heating, your air conditions, your refrigerators, your televisions, your motors, whatnot. So most of our requirements require energy, and that too electrical energy. So power system is a network, largest man-made network, which aims at providing quality electrical energy to all the customers who are connected to it, who are connected to the utility. Understand? So it is ever expanding. Every day some new industries are coming, new buildings are coming, new colonies are coming. So everyone requires electrical energy that we must be able to provide. Understand? So this network, the power system network, is every day it is expanding in all possible directions. Understand? So in power system network, it consists of generation, transmission, distribution, and protection of the system. Okay. Now, so it contains many devices, many devices. For example, for generation, we require synchronous generators, transformers to step down or step up the voltage, circuit breakers for protection, relays, transmission lines, insulators, okay, motors, okay, understand? So all these components that are connected or that are the integral part of the power system, they are called power system components. Okay. Now, before going forward, we should be familiarized with the few terms. First one is called utility. First one is called utility. So, what is the utility from which you are getting your electrical energy? I'll tell you. In Tamil Nadu, you are getting from Tangedco. Tangedco, Tamil Nadu Generation and Distribution Corporation. Understand? So, what is the utility then? How do you define utility? The entity or a body that does the generation, transmission, and distribution of electrical energy and brings the electrical energy to the customer premises. The entire body is called utility. In Andhra Pradesh, it is APEPDCL. In Kerala, it is Kerala State Electricity Board. Understand? So, like this, the entity that is doing all this generation, transmission, distribution, and bringing down the energy, electrical energy to your premises is called utility. So from where the scope of utility ends, the scope of utility ends till your energy meter. That means the two, if you are a single phase customer, one phase and one neutral will enter into your energy meter. Understand? So till that point, it is the scope of utility. Utility is responsible till that point. Once the electrical conductors enters after energy meter, it is the responsibility of the customer to take care of the safety as well as the protection of the electrical system. Understand? No, customer. Who is the customer? The person who pays the money and buys this electrical energy is the customer. Understand? So we are all the customers. A cinema, a movie complex, a shopping mall, a residential complex, a gated community, an apartment, all these are customers who pay the tariff to buy the electrical energy. So there are different types of customers based on the utility. Domestic customers like us, household customers, we call them as a domestic customers. Commercial customers like shopping malls, multiplexes, uh, the big shops and all that, they come under the commercial category where the tariff would be little higher. Okay, domestic tariff would be little less, commercial tariff would be higher. Industrial customers, that means a small scale or a medium scale industry uh, which takes the electrical energy, which purchases the electrical energy from the utility. They are the industrial customers. Understand? The scope and responsibility of the customer is after its metering station. Okay. In case of a big industry, there will be a first, once he may be taking the electrical energy at 11 kV or 33 kV. So once the 33 kV line enters, there will be a metering panel. So after metering panel, he'll step down the higher voltage to his required voltage, and then he will distribute in his industry or the shopping complex or something it is. Okay. That is the basic idea of utility and the customer. Who is utility and who is the customer? Okay. Now it's a basic schematic diagram that explains how, in general, how the power system would be. So if you can see here, the generating stations, which will be usually located at remote locations where the most of the generation in India happens through coal. Thermal generation happens mostly in India out of the all the electricity that we generate, 70% of the electricity generation is from the thermal. And next biggest contributor is hydro, which contributes around 13% of the total electrical generation. Then comes the nuclear and other this one greener forms of electrical energy generation. Uh, in the last, I'll give a brief scenario of the uh, industry scenario, the how the generation is happening, and what are the future objectives of the Indian electrical industry. All that we'll discuss at a later point of time. Okay, so if you can see in the figure that there is a pond and there is a thermal generating station here, if you can observe. So most of the generation in India is coal based, and then the next major chunk is contributed by the hydroelectric generation. And you'll be learning in your machines and all that stuff that we cannot generate the voltage at very high voltages. Okay, because I'll give you brief reason. Your machine sir will give more details. Because the size of the stator becomes very high, and the amount of insulation that we require to provide between the stator slots of the generator also increases. So the size cost of the alternator increases abnormally if you go for high voltage generation. So practically all over the world, the generation happens below 30 kV only, because practically it is not possible to generate electrical energy at a voltages beyond 30 kV. Okay, so this is the scenario. The highest voltage where we generate the voltage is around 30 kV. In India, it is around 22.5 kV, that too in Tamil Nadu, Kudankulam nuclear power plant. The largest generator in India right now is stationed in Kudankulam nuclear power plant, which is around 1000 MVA. 1000 MVA, and the voltage at which it is generating is 22.5 kV. You can search in Wikipedia or Google about the alternator ratings of the Kudankulam nuclear power plant. Understand? So because there are some limitations of the size and cost of the alternator, so it is not practically possible to generate the voltage at very high voltages. Okay, but due to economic considerations, hello, are you able to follow, gentlemen?
Yes, sir.
Yes, sir.
Are you comfortable with my language?
Yes, sir.
Okay. So the next thing is that for various factors, and mostly because of the economic reasons, we wish to, or we aim to transmit the power at high voltages. High voltage transmission of electrical energy is very economical. It will save a lot of cost. Understand? So for that, we definitely after the generating station, there will be a transformers to step up the voltages from the generating voltages to the very high transmission voltages. So, and next, the primary transmission happens. The primary transmission can be anywhere around 220 kV to 765 kV. And then there will be secondary transmission, because once you have transmitted to the load center where there is a chunk of load that is connected, then you have to step down the voltage to the utility levels. So primary transmission is mainly aimed at evacuating the electrical energy to the longer distances. Suppose one power plant is at, say, Singareni, near Singareni, one power plant is there. It has to transfer that electrical energy to, say, Kolkata, which is around 400 kilometers or 500 kilometers. Then you will be transmitting this electrical energy at a higher voltage, say 400 kV line or 765 kV line, because that will be economical. Once it reaches the premises of Kolkata, then you have to step down to the medium voltages so that you can transfer it to the nearest substations inside Kolkata or in the vicinity of Kolkata. So then the medium transmission or the secondary transmission comes into picture. Understand? So here in the picture you can see the primary transmission is happening at 220 to 500 kV, 220 to 500 kV. Nowadays it can go up to 765 kV. And then after primary transmission, you can see that this is the primary transmission that is happening. Again, there is a step down transformer where it is stepping down from the 220 or 500 kV to 132 or 66 kV. Understand? Again, this transmission that happens from here is called secondary transmission. And from the secondary transmission, once it reaches the substation, again it will be stepping down to any to 11 kV or 33 kV depending upon the requirement. Okay, so this is a substation in the outskirts of a city, outskirts of a town or city, and these are the substations at the various strategic locations inside the town, inside the city or town. Understand? So from there the electrical energy will be distributed to the local area. So from there the primary distribution happens. So this primary distribution will bring the electrical energy to your street corner. Okay, from that street corner again the voltage will be stepped down from 11 kV or 33 kV to 415 volt. That 415 volt secondary distribution network will provide electrical energy to the local customers or local shops or something like that. So you can see that many elements are involved in this complete power system. One is the generating stations and many auxiliaries in the generating station, transformers, transmission line, transmission towers, insulators. In this schematic diagram, we have not shown the protection schemes, circuit breakers, relays, fuses. So many components are involved in this power system network. Understand? So any doubt you can ask so far?
Sir, initially, why we are stepping up to that much high voltage? Can you explain that one, sir?
We'll come back to ma'am. That is the complete transmission. We'll be learning it. There is a complete chapter devoted to why we are stepping up to such a high voltage and what are the advantages of high voltage transmission. Most probably in the third lecture will come to all this. Okay, just to tell you, if we go for higher and higher voltage transmission to transfer the same amount of energy, the conductor size will drastically come down. The size of the conductor that is required to transfer the energy will come down. So which will save a lot of money by saving the conductor material. Okay, and high voltage transmission also ensures the stability of the power system network. There are many other advantages which we'll learn gradually. Okay.
Okay, sir. Thanks.
Any other question, gentlemen, ladies and gentlemen? Then now can I ask one question? What is the voltage that you are getting in your household? 230 volt. 230 volt RMS, phase to neutral voltage. Understand? So it is 230 volt RMS, phase to neutral voltage. Okay. Suppose if you are a big customer, suppose you are having a 3-bedroom house along with 3 bathrooms, and every bathroom is having a geyser and every bedroom is having an air conditioner. Then as an electrical engineer, would you prefer a 3-phase supply or a single-phase supply to your house?
3-phase, sir.
3-phase. Why?
Because the power consumption is more.
Yeah, power consumption is more. Why can't I take single-phase supply? So why do I require 3-phase supply? Think about it. Okay, it is advisable or it is mandatory to take 3-phase supply after a point of time. Why? Because if you take the same energy from a single phase supply, the amount of current which you draw will be very high. Suppose one AC is drawing say 10 ampere current, one geyser is drawing say a 12 ampere current. So if all of them are connected in the same phase, the amount of current that flow through your phase conductor and return through neutral conductor will be very high. As a result, there will be more losses, and moreover, your size of your phase and neutral conductor should also be bigger. Okay, so there will be voltage drops, more losses, and the size of the cable that is required increases. So that's why we go for the three-phase supply, because now the load is equally distributed among three phases. So the size of conductor will be less, the losses in the conductors will be less, the voltage drop in the conductor also will be less. These are the advantages. Okay. Now this is about the primary and secondary distribution, which I've explained. So primary distribution starts somewhere around 66 to 132 kV, and then this is a distribution transformer which is in the vicinity of your streets. In the corner of your street, you will be having a distribution transformer. So that is this distribution transformer, which usually steps down either 33 kV or 11 kV to 415 volt. And then say till this point in the power system network, only three conductors will be there. It is all three-phase, three-wire transmission till this point. So from your local distribution transformer only, the neutral conductor will start. There won't be any neutral till that point of time. The neutral will start only from the local distribution transformer. Understand? Why, we will discuss later. Okay. So all the transmission happens through three conductors only. There is no neutral in the transmission of electrical energy. Understand? One more important point which I want to tell here, we study power system from the perception of utility. From the perception of utility. Utility means we assume that we are the utility. Okay. So we study power system from the utility point of view. So what is the benefit to us? Whatever benefits the utility is the benefit to us. You remember that you are utility, you are studying the power system from the point of view of the utility. Okay. The next definition you must be aware of is the nominal voltage. Nominal voltage designated by Vn. So what is the nominal voltage? Tell me. So I asked a question previously. Somebody answered that in our house we will get the 230 volt RMS voltage between the plug point. Okay. Now, if you take a multimeter and measure the voltage between phase and neutral, it will never be 230 volt. It will never be 230 volt. Either it will be less than 230 or it will be in excess of 230. You take 100 readings in a day at different point of time. It is very rarely that you will get 230 volt. Okay. So now the actual voltage that you are measuring in your plug points in your house is called actual voltage, V actual. V actual. Understand? But the voltage that we are supposed to get in the plug point is called nominal voltage. Is called nominal voltage. Understand? So the voltage that we are supposed to get at any point in the power system network is called nominal voltage. Is called nominal voltage. So this nominal voltage and actual voltage will be different. Because the voltage in the power system network is continuously fluctuating. Okay. Similarly, to get 230 volt in your household sockets, household 3-pin sockets, what should be the voltage in the distributor that is running in front of your house? What is the Nominal voltage of the distributor that is running in front of your house. Can anyone? That is let us assume this is the distributor that is running in front of your house. Then what should be the voltage that you should get between the two conductors in this distributor?
400 volts.
How much?
400 volts.
400 volt. 400 volt, or sometimes it will be 415 volt. So this voltage that you are telling it is 415 volt is called a nominal voltage of the distributor. Now if you look back at the primary side of this transformer, secondary side you are getting 415 volt. You are supposed to get 415 volt. Now tell me, what is the primary voltage? It is 11 kV or 33 kV. 11 kV or 33 kV. So this is called the nominal voltage at the primary side of the transformer. If you go and actually measure the voltage, it may not be 11 kV. It may be slightly higher than 11 kV or lower than 11 kV. So nominal voltage is a voltage that we are supposed to get at any point in the power system network. But there will be slight difference between the nominal voltage at that point and the actual voltage at that point. Okay. The second important point is all the voltages, that is 11 kV, 415 volt, 230 volt, all the voltages that we are expressing are line to line RMS voltages, except for the voltage at the plug point in your household where you are measuring between phase and neutral. All other voltages are line to line RMS voltages. In your household plug points, you are measuring phase to neutral RMS voltage. Okay, gentlemen, just give me 2 minutes break. I'll come back. You can jot down these things if you want. I'll just come back in 2 minutes. Huh? Please excuse me for this. Yeah, hello. Are you able to listen to my voice?
Yes.
Okay.
Yes, sir.
So this is regarding the nominal voltage. Next. So our power system is basically a business where we are selling the electrical energy, isn't it? So by selling the electrical energy, we are making the money. Understand? So electrical power system is nothing but a business between. Tell me, for any business, there should be two parties between the utility or supplier. The other name is customer. Customer. So what is the quantity that we are, what is the product that we are selling? We are selling the electrical energy. Understand? So tell me, what is the unit of electrical energy that we are selling? What is the unit of electrical energy that we are selling? In mangoes, we'll sell in hundreds or dozens. Likewise, rice will sell in kilograms. Electrical energy will sell in units. So the fundamental unit of electrical energy that one unit is called kilowatt hour. Kilowatt hour. Kilowatt hour. Understand? So 1 kilowatt hour is equals to 1 unit. 1 unit of electrical energy. Sir, as far as I know, the unit of energy is joule or calories or kilocalories. But how can 1 kilowatt hour be the unit of energy? It is very simple. Kilo means 10 cube. There is no other meaning for kilo. Kilo means 10 cube. Watt is the unit of power. Hour means 3600 seconds. Understand? So it will become how much? 3.6 into 10 power 6. 3.6 million. Watt into second is joule. Watt into second is joule. Understand? So 1 unit of electrical energy, that is 1 kilowatt hour, is equals to 3.6 million joule of energy. Joule of energy. That means for taking 3.6 million joules of energy, we are paying some 6 rupees or 7 rupees or 4 rupees depending upon your tariff slab. Understand? So it is basically a business between the utility and customer. We are selling a product called electrical energy and the unit is kilowatt hours. Now tell me, what are the objectives or aims of utility in this business? Anyone? What are the objectives of utility? Aim, utility or supplier? Please speak. That would make the session more interactive.
Profit, sir.
Profit. Ultimate motto is the profit. Next, only profit would suffice. Any other objective? Suppose you are the entrepreneur. Basically, you do business to make profit. Only profit is sufficient. You don't want anything else.
The quality.
You want to give quality. How you ensure that you are giving quality?
Reduced losses or
Customer satisfaction. That's it. If the customer is satisfied with your product, that speaks for your quality. Understand?
yes.
So the second thing is customer satisfaction. The other name for beautiful name for this customer satisfaction is brand value. Brand value. Okay. So all business people, they care for profit and brand value. In fact, more initially in the business, they'll care for the brand value more, because once you establish a brand value for yourself, then customers will continue to flow. Understand? So these two are the primary objectives. Whereas in our business of power system, what is happening, since there is no competition, so the only aim for them is to make profit, Understand? Okay, if there is no competition, if there is monopoly in the market, then since the customer don't have the alternate choice, they'll not focus on the second factor. They'll only focus mainly on the profit. Now, coming to the customer point of view, what are the objectives or what are the desirable features of customer in this while buying the electrical energy? Just tell me. What customer wants? Anyone?
Like no interruption.
Quality.
I heard two answers. Correct me if I'm wrong. The first answer is no interruption. Second answer is quality. Am I right? Yeah.
Yes, sir.
Yeah. No interruption. That means uninterrupted power supply. 24/7 the electrical energy should be available at my premises for my utilization. So this is called, the other beautiful word, this is called reliability. 24/7, whenever I want, how much ever I want, that much electrical energy should be available at my premises so that I can use as per my requirement. Second thing is quality. We'll discuss about quality of electrical energy in the next coming slide. Only two things enough? In India, the first thing that comes ahead of these two is the cheap. It should be available at cheaper rates. It should be available at cheaper rates. So mainly customer who is buying electrical energy, his aspirations are, he requires uninterrupted power supply, that is reliable power supply. Second thing is quality power supply. The third one is it should be available at cheaper rates. Understand? So these are the aspirations of customer. These are the aspirations of the supplier or utility. Okay. Now, what is quality electrical energy? What is quality electrical energy? Yes, you're all electrical engineers. How do you ensure the quality of electrical energy? Anyone? You can tell wrong answer also, nothing wrong. I'm not evaluating you. I'm just trying to find out what you know. How do you define quality of electrical energy?
Without loss, and there is no voltage structure.
Without loss. And second thing, ma'am, what do you say?
There is no voltage drop.
Very good. No voltage drop. Let me hear from other students as well. See, I just want to know your perception of electrical energy quality. Everyone will have different viewpoints, isn't it? Yes, yes. Anybody else? Anyone else? No one? Very poor. You should at least talk to me, right? Then I'll ask Bhuvan. Bhuvan, what do you think? Mohana Priya.
The input energy, input energy, we have to get it in output side also.
Input energy we have to get in output. That means you mean to say higher efficiency.
Yes, sir.
Higher efficiency. Next, anybody else?
It should consume the energy supplied.
We should consume the energy supplied. So there should be no wastage of energy. No wastage of energy. Yes. See how many different viewpoints we are getting. You should talk. Anyone else you're having with different idea?
No frequency deviations.
So no frequency fluctuations. Okay. Yeah. That's it. See, who requires quality electrical energy? Customer. Customer wants quality electrical energy. So why does customer wants electrical energy? He wants to use this electrical energy to run his appliances. He wants to run his fan, he wants to run his induction motor, he wants to run his AC, fridge, everything. Understand? So if you look the quality from the point of view of customer, he is not worried about losses. If the losses are more, then it is a loss to the utility. Customer is not bothered. What are your transmission losses? What are your efficiencies? Customer is least bothered. Okay. Yes, customer is worried about the wastage of energy also. It doesn't matter for him. So for him, what matters is whatever the voltage that you are providing to him, it should be free from the fluctuation. Whatever you are promising that you will provide 230 volt, you should supply 230 volt, or at least 229, 228, or 231 or 232. Okay. Second one is his equipment. If you see any electrical equipment, they definitely they will give voltage at which it will operate, frequency at which it will operate, and how much current it will take. So since all the equipments are designed to operate at a fixed range of voltage and fixed range of fixed value of frequency, in frequency there is no range. In voltage there will be certain range, but in frequency it is designed to operate at a fixed frequency. So customer wants what? Less voltage fluctuation, I can say, because zero voltage fluctuation is impossible. Very less voltage fluctuation, absolutely no frequency fluctuation, and whatever the voltage that he is getting, it should be free from harmonics. Free from harmonics. That means you should get a pure cosinusoid or sinusoidal voltage waveform. Okay, so from the point of view of customer, the quality is defined by three factors. One is lesser voltage fluctuation, no frequency fluctuation, and the pure sinusoid wave you should get in the form of the in voltage. Understand? So, but the transmission losses, the efficiency of the transformers and generators, and wastage of energy, these are all the concerns of utility. From the utility point of view, these points are valid, because if I waste my energy, my revenue will come down. If I operate my equipment at higher efficiency, lower efficiencies, then I require more equipment to perform the same function. Understand? Since we are studying the quality is the requirement of the customer. So from the point of view of customer, quality is defined by three factors. Voltage should be within plus or minus 6% of the nominal voltage, plus or 6 minus. This value of the tolerance will change from state to state, utility to utility. In Kerala, if their power system network is strong, they may allow lesser voltage fluctuation. In some other state, where like Uttar Pradesh, where the power system is poor, they may allow 10% tolerance. So this value is roughly have taken. This value will change from utility to utility. The voltage should be within plus or minus 6% of the nominal voltage. That means you should get 230 volt in your plug point. If the voltage is plus or minus 6% of this 230, then I can say that my voltage profile I'm getting is good. My voltage which I'm getting is good. My voltage profile is good. Understand? Frequency should be plus or minus 1% of the nominal frequency. That is your actual frequency, that should be equal to nominal frequency plus or minus 1%. What is the nominal frequency in India? 50 hertz. 50 hertz. So if your actual frequency is 50 hertz plus or minus 1%, that is in the range of 49.5 to 50.5 hertz, then your frequency is good. Whatever frequency you are getting is good. Understand? Similarly, if you are 11 kV customer, your voltage should be 11 kV plus or minus 6%. Then you say my voltage profile is good. Understand? The third point is nominal frequency in India is 50 hertz. So allowable range is 49.5 to 50.5 hertz. And the last factor is the sinusoidal voltage wave you are getting should be free from harmonics. So these three factors govern the quality of electrical energy from the point of view of customer. Okay. Next. What are the challenges faced by the utility in supplying the quality electrical energy? What are the challenges faced by the utility in supplying quality electrical energy? Understand? So, as you say, to maintain a frequency of 50 hertz, to maintain a constant frequency or the of 50 hertz, we have to maintain real power balance at all the time. We have to maintain the real power balance at all the time. That is, at each and every instant of time, our prime mover input power should be equal to generator output power. Generator output power. Why? Because we'll discuss about this in more in stability. Roughly, in as a layman, what I'm going to tell. Suppose in our power system there are 10 big generating stations. So the total power generator is I is equals to 1 to 10 PGI. This is the total real power generated by all 10 generating stations. This value should match to the total load, electrical load existing in the power system network plus total losses. This equation should be valid for each and every instant of time. That means there should be an absolute balance between the amount of real power generated, the total power demanded by all loads put together, and total losses in the transmission lines and distributors and etc. If this balance is maintained at each and every instant of time, then what happens? Your actual frequency will be equal to your nominal frequency, that is equals to 50 hertz in India. Okay, understand? Why sir, why it is difficult to maintain this equilibrium? Why? Because to control the generation, we have to control the input supply to the turbine. If it is a steam turbine, you have to control the amount of steam flow to the turbine. If it is a hydro turbine, you have to control the speed and the velocity of the water jet into the turbine. Okay, understand? But this load is not in our control. We can control the generation, but this load is not in our control. Why? Because the next moment who will turn on which device, who will turn off which device, we cannot predict. Suddenly I feel like switching on my AC, so I'll switch on, and somebody may want to switch off his television, switch off his motor, or there may be some fault in the big industry. Suddenly some big industry that is running continuously, because of some short circuit, it may trip. So once it trips, what happens? The load on our power system will suddenly getting down. So the load on the power system is never constant, because depending upon the customer requirements and faults, this load, P load, will be continuously fluctuating. P load will be continuously fluctuating, either increasing or decreasing. So how much time the load take to fluctuate? Instantaneously. Load will change instantaneously. But to change the generation, that means to increase or decrease the generation to maintain this equilibrium, it will take some time. Why? Because we have to increase the coal input to our boiler, and then the steam input to the turbine, hydro input to the turbine, some valves have to be changed. So adjusting to the load fluctuation, adjusting the turbine input to the load fluctuation will take certain time. So there is always this makeover process that is happening. The load is continuously changing, and we try to change our generation according to the load. So there is always some imbalance between. Understand? So that's why our frequency will be continuously fluctuating. But however, the things are streamlined such a way that this fluctuation is not more than 1%. More details we'll discuss about these concepts in power system stability. Okay. So adjusting the generation according to fluctuating load is the main challenge, which will lead to the frequency fluctuation. Any doubt here, gentlemen? Hello.
No, sir.
What is the prime mover? Sir?
What is a prime mover?
Yes.
Okay. How does a generator generate a power? We need to rotate the rotor of the generator, right?
Yes, sir.
At what speed? Depending upon your poles. If it is a 4-pole machine, we have to rotate it at 1500 rpm. If it is a 2-pole generator, we have to rotate it at 3000 rpm, which is called synchronous speed. Okay, 120 into F divided by P, that will give you the synchronous speed. Understand?
Yes,
so who is rotating that generator? The shaft of the generator is coupled to some device which rotates that rotor of the generator. Understand? You will be coupling the shaft, that means you will be coupling the rotor of generator to a mechanical device which does this rotation. That mechanical device to which your rotor shaft of the alternator or generator is connected, it is called prime mover. The prime mover is nothing but it can be hydro turbine, wind turbine, or steam turbine. Understand?
Yes, sir.
Okay. Next. So that is the difficulty in fixing the frequency. Now, to fix the voltage to their nominal values, that means to fix the voltages at all points in the power system network to equal to their nominal voltages, we have to maintain reactive power balance in the power system all the time. That means again, the reactive power generated in the power system network should be equal to the total reactive power demanded by all the loads put together and total reactive power loss in the transmission. So this reactive power can be generated by whom? It can be generated by generators, capacitors, and various other devices like phase modifiers, war generators. Okay. So all this reactive power generated by all the elements connected in the power system should be equal to the reactive power load. This reactive power is mainly used by induction motors, transformers, transmission lines. Okay. So all other inductive loads, they require reactive power. And even the reactive power losses occur in the transmission lines. So if you maintain this equilibrium at all the time, then what happens? Then your actual voltages the actual voltage magnitudes will be equal to the nominal voltage magnitudes. Nominal voltage magnitudes. For the, again the same reason stated, the load is not in our control. Load is not in our control. So we have to again catch up. We have to adjust our reactive power generation depending upon the load fluctuation, which is a challenge, which will lead to voltage fluctuation, So real power balance is responsible for frequency. Reactive power imbalance is responsible for voltage fluctuations in the power system network. Understand? So apart from these two challenges, what are the other challenges faced by electrical power system? Till date, there is no invention or discovery regarding the bulk electrical energy storage. Bulk electrical energy storage is not possible till date. Yes, we are able to store some amount of electrical energy in our batteries of smartphone, batteries of inverters, or big batteries that we use in solar power plants. Okay, but only few megawatt hours of energy we can store, or compressed air plants and all that. We can only store some small packets of energy. Bulk energy, bulk electrical energy storage is still not possible. That means what? Whatever energy you generate at this point of time, you have to transmit, you have to consume at the same point of time. You have to transmit and consume at the same point of time. So we cannot store the electrical energy. That is the main disadvantage. So if your fan is running right now, the energy that is required to rotate your fan has to be generated, transmitted at the same instant of time. That's why your electrical energy travels at the velocity of light, nearly at the velocity of light, because your generating station will be some 3, 4, 500 kilometers away from your fan, but still it runs. Why? Because it travels nearly approximately at the velocity of light. The electrical energy has to be generated, transmitted, and consumed at the same instant of the demand. Okay. There is no provision to store electrical energy in bulk quantities. Still, the research is going on. Maintaining the voltage and frequency fluctuations of power system within the operating range while meeting the load fluctuation is the biggest challenge. So we have to, in order to provide quality electrical energy, our voltage fluctuation should be plus or minus 6% of the nominal voltage, and our frequency fluctuation should be plus or minus 1% of nominal frequency. To maintain this voltage and frequency within limits while meeting the fluctuating load on the power, while meeting the fluctuating load is the biggest challenge of the electrical power system. Maintaining high reliability and safety, because we are so much dependent on electrical energy nowadays. We cannot afford long outages of electrical energy. Suppose the complete Chennai city is out of electrical energy for 24 hours. Imagine what would happen. If it happens for 48 hours, 25% of the people will become mad. Why? Their mobile phones won't work. Understand? So we are so much dependent on electrical energy that we take it for granted. Just like air we breathe, does we take care of that our nose is functioning properly, whether my inhalation and exhalation are properly going? Will you spend time and observe? No, because you think it will happen naturally. You take it for granted. Likewise, we take it for granted that the electrical energy is available and will be available forever. Okay. So in order to ensure this, we have to maintain high reliability and safety standards for the power system network. One more challenge is reducing the cost of generation and maintaining high transmission efficiency, optimum utilization of the installed generating capacities. So all these are the major challenges that are faced by the electrical power system. Okay. So any doubt till this point, gentlemen? Hello.
No, sir.
So this is a brief introduction of the electrical power system. Okay. Now you can take 5 minutes break if you want. We'll continue with the mathematical portion. This is an introduction portion. Uh, then we'll continue with the some basics, mathematical basics that we require to analyze the power system. For every one of you, this AC circuits is completed.
Yes, sir.
Okay. So when I'm telling some topic, if you are aware of it, just pause me. I'll skip it and we'll continue. So you can take 5 minutes break and you can come back. Okay. Thank you. Hello, welcome back. Am I audible? So
Yes, sir.
we'll discuss few properties that we require. So it is a cosinusoidal signal, as you can see, voltage signal. V of t is equals to a cos omega t plus phi. Now, what is a here? What is a? What is omega?
Magnitude.
What is phi and what is cos? So it is a time variant voltage signal. So where a is the amplitude, and omega is what?
Angular frequency.
Very good. Angular frequency. What is the unit?
Radians per second.
Radians per second. Radians per second. Very good. What is phi?
Phase angle.
Phase angle with respect to reference. With respect to reference signal. Reference signal or reference wave. Okay. What is the cause? Nature of waveform. Nature of waveform. Okay. So A is the amplitude of the signal. Omega is the angular frequency in radians per second. Phi is the phase angle with respect to phase angle difference with respect to the reference signal, and cos is the nature of waveform. Okay. Now, the second important thing is you might have studied what is a linear network. What is a linear network? Tell me, what is a linear network or linear circuit, whatever you learned.
Circuit which obeys superposition.
Circuit which obeys superposition and homogeneity. Understand? Circuit which obeys both superposition principle as well as homogeneity principle is called a linear network. Okay. So what are the linear networks? A linear network is a network that contains all linear elements, isn't it? As simple as that. Okay. So linear network obeys homogeneity principle as well as superposition principles. Okay. Now, for this, in our power system network, you can see very simple. Most of our elements are only RLC elements only. Resistor, inductor, and capacitor only we are having. So all the elements will model in terms of resistor, inductor, and capacitors. And our voltage sources are AC voltage sources, that is cosinusoidal voltage sources. So all are linear elements. So all our power system networks are linear only. All our power system networks are linear only. So for this linear power system network, what I am doing, I am applying a voltage of, say, V1 of t. And in one particular branch, I am calculating the response. Let this branch is, say, RL, load resistance. So the current is, say, I1 of t. Okay, this is a complete linear network. So what is my V1 of t? V1 of t is, say, A cos omega t plus theta. A cos omega t plus theta is my V1 of t. Then let us say my I1 of t is, it is let us call this one as amplitude is B cos omega t minus phi. Okay. Now you can observe that when you excite any linear network, with a cosinusoidal voltage source. That means cosinusoidal means either a cos source or sine source, sine wave or cos wave. Then what happens in the response can be a current through a branch or voltage across a branch. So what you will calculate in entire circuit theory, you will calculate some current, some current somewhere or voltage somewhere or power somewhere, isn't it? So power is a non-linear quantity. So the response mostly will be current through a particular element or voltage across a particular element. In that case, what you can observe, so when you excite a linear network with a cosinusoidal source, the two things that may change in the response are what is changing? The amplitude is changing. The amplitude is changing because the amplitude of excitation, amplitude of response are different. The second quantity that is changing is the phase angle of the signal. Understand? So the remaining two quantities, that is the nature of waveform and the frequency of the signal, angular frequency, they are remaining same. They are remaining same. So this is a fundamental thing which you have to remember. The mathematical derivation is there. We are not going to do that. Simply vaguely remember that whenever you excite a linear network with a cosinusoidal source, in the response, the two parameters out of four may change and the two parameters remains the same. Okay. So out of these four parameters, the angular frequency and the nature of waveform will remain same in the source and excitation, but the amplitude and the phase angle may differ. So what from this, what I can get is what information I can get is, so if we know the information about the amplitude of the signal and phase angle of the signal, that is good enough to recreate the original signal. That is good enough to recreate the original signal. Understand? So while representing these voltages in phasor form, we only take the amplitude and the phase angle. Why? Because the remaining two things, that is the nature of waveform and the angular frequency, will remain same. Understand? So yes. When a linear network is excited by a cosinusoidal source, the response in any branch retains the nature of waveform and frequency, and the two properties that may change are the magnitude and the phase angle. This is the main basis for creating the concept of phasors. You might have studied phasor analysis or phasor diagrams in your circuit theory. Have you studied, gentlemen? Excuse me.
Yes, sir.
You have idea about phasors?
Basics.
No, I'll just give a simple example. You tell me 10 cos 100 pi t plus 30 degrees. So many volt. What is the phasor equivalent of this signal? It is a time domain signal. Now tell me what is a phasor signal for this one?
Ten by root 2 at an angle
10 at an angle 30. 10 at an angle 30. Isn't it? That's why so many volt. That's how you represent it in a phasor. Okay. Yes or no?
Yes, sir.
Now V2 of t is equals to 2 sine 100 pi t minus 30 degrees, so many ampere, sorry, so many volt. How do you write this signal?
2 at an angle minus 30.
Sure, think.
What an angle minus 30.
Sir, first we have to convert the sine into cos.
Very good. First, we have to convert this sine into cos. Understand? So then only you can tell the phase angle. So how to convert this sine into cos? So it will become how much? 2 at an angle minus 120. Sir, how you have done it? Very simple. Which wave starts first, cos or sine? Cos will start first. Just 1 minute. Yeah. The sine wave is lagging cos wave by 90 degrees. So to convert the sine to cos, I am adding minus 90. Understand? So, are you able to follow, gentlemen? Hello?
Yes, sir.
See, when you are comparing the phase angle between any two signals, you have to ensure three things. You have to ensure three things. The phase comparison is only possible if both signals should have same angular frequency, that is omega. Then only you can compare the phase angles, otherwise it is impossible. One signal is having cos 100 pi t, the other one is having cos 200 pi t, then you cannot make the comparison. The second one, both signals should have same nature of waveform. Either both of them should be cos, either both of them should be sine. Nature of waveform should be sine. And the third and most important thing is the polarity should be same. Should be same. Then only we can compare the phase angle. That means both signals should be either positive or both signals should be negative. You cannot compare the phase angle between one positive signal and other negative signal. Understand? So you have to ensure that all these three things are same, intact, while you are comparing the phase angles. Here, what is the violation? Both signals are positive, both the frequencies are same, but however one is a sine waveform, the other is a cos waveform. So when you're speaking about the phase angles, then you should convert them into the same format, same nature of waveform, and then you tell. Okay, when I say what is the phase angle between V1 and V2, you can clearly say that V1 is leading V2 by 150 degrees. V1 is leading V2 by 150 degrees. So these are some important points which you have to remember, So whenever we are converting a signal from time domain to phasor domain, we are only taking the information of amplitude and the phase angle. Why? We are assuming that it is always a cos waveform, not sine, gentlemen. Cos is the reference. We are assuming that our waveform is a sinusoidal waveform. and our angular frequency omega is constant. Our angular frequency omega is constant. Understand? You have to remember these very important points. So the second important point which I want to tell you is that when you draw a phasor diagram, let us say V is equals to 10 at an angle 30 degrees, so many volt. How you draw the phasor diagram? This is real axis and this is imaginary axis. So your phasor diagram will be how it looks like. 10 at an angle 30 degrees. This is your V. Am I right? The amplitude of this V is 10. Okay. Are you able to understand?
Yes, sir.
But in the phasor diagram, you remember, you always have to mention an arrow stating omega radians per second. You should never forget. If you don't write this symbol, then your phasor diagram is incomplete. This is not a fixed quantity. This quantity is continuously rotating. This quantity is continuously rotating in anti-clockwise direction at omega radians per second. At omega radians per second. It is continuously rotating in counterclockwise direction at omega radians per second. Understand? So this is a phasor quantity. This is a phasor quantity. So sir, then what we are, since it is continuously rotating, sir, why we are only writing this one? Why cannot we write this like this, like this, like this, or like this? Okay, so this quantity, since it is continuously rotating, we are taking the reference of this signal, this rotating quantity at t equal to 0. That means we are taking the snapshot of the rotating quantity when time t equal to 0. When time t equal to 0. Understand? So that is the phasor quantity which you are drawing in the phasor diagram. So to explain it more clearly, if you take the voltage signal, the time domain signal for the same one, how do you recreate the time domain signal? The 10 will remain 10. The reference waveform is cos. This is omega t plus 30 degrees. This is the time domain signal and this is the phasor signal for the same thing. Now if you draw this signal, if you draw this signal at t equal to 0, what is its value? At t equal to 0, its value is 10 cos 30. 10 cos 30. What is cos 30? 10 into root 3 divided by 2. So in this phasor diagram, if you take the real quantity, this real quantity is 10 cos 30. This quantity is 10 cos 30. Understand? Imaginary part, that does not exist. Only for our mathematical convenience, we create an imaginary part, but in real world, there are no imaginary voltages. Understand? So you can correlate that whatever phasor diagram you are drawing is the snapshot of the continuously rotating quantity at t equal to 0. At t equal to 0. Understand? So all the quantities, whatever you draw in phasor diagrams, they are not fixed quantities. They are continuously rotating in an anti-clockwise direction at omega radians per second. So whatever you are projecting in a phasor diagram is their value, their position at t equal to 0, at time t equal to 0. Understand? So gentlemen, any doubt you can pass me and you can ask, because these concepts are very essential for electrical engineers. Okay. So to give a better idea, just I require one empty slide. Just a minute, I'll create a slide.
Sir,
Yes, ma'am.
sir, in phasor signal 10 by root 2 only will come now, sir.
I did not mention any RMS phasor as of now. Now we are taking actual phasors like this. When you tell that our phasors into RMS phasors, then we have to scale the amplitude by root 2 factor. That means we have to divide the amplitude by root 2. Understood, ma'am?
Okay, so that then it's actual phasor.
Now, so far we are discussing the actual phasors, but in practice we always draw for the RMS value. So every amplitude of the phasor gets scaled, that is gets divided by a root 2. Okay, that
Okay.
I will tell in the next coming slide. Because
Okay.
introducing all at a time may create confusion.
Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Yes. Yeah. Now, just for your understanding, need not take this seriously. So if I draw the cos signal, so this is the phasor diagram, and if I draw the cos signal, let us say this is the reference axis. I'm using a different color for cos signal. Yeah. What happened? So if you take a reference cos signal, it would be something like that. Okay, and it will continue. So let this amplitude be say 10. Let this is be minus 10. This is omega t axis. So this signal will become V of t is equals to 10 cos omega t. Okay. Now if you draw the phasor diagram for this one, let us, this is the real axis and this is the imaginary axis. Minus g plus g. Okay. Now, how do you denote this cos signal? How do you denote this cos signal? You denote this cos signal in phasor as 10 at an angle 0. 10 at an angle 0. So this cos signal is in positive real axis. Yeah. How to draw this one? 1 second. Let me change this thing. This is minus j plus j plus j minus j, positive real and negative real axis. How do we draw this one? This is the signal 10 at an angle 0. Now, after this, what will happen? In this time domain signal, after a 90 degrees, it is coming to this point. So the same can be correlated as it is rotating 90 degrees and it is coming here. So this is the signal after 90 degrees. Okay. Now if we can see at t equal to 0, what is the value of this signal at t equal to 0? It is 10 cos 0, that is equals to 10. What is the real value? 10. Now once it rotates 90 degrees, once this time domain signal shifts 90 degrees, then what is its instantaneous value? 0. Now at this, when the phasor is in this position, what is the real value of this phasor? It is 0. Understand? So again, if this time domain signal shifts by 180 degrees, it is equivalent to this signal rotating to this point. Okay, then what is its instantaneous value? Minus 10. If you can imagine, for this phasor at this position, the value of the phasor is minus 10 comma j0, which is minus 10. The real amplitude is minus 10. So like this, once again it rotates to one more 90 degrees, then its position will become this position. So one counterclock rotation in the phasor domain is equal to one time period in the propagation of the wave by one time period in the time domain. So one anti-clockwise rotation, one anti-clockwise rotation of signal in phasor domain, phasor or frequency domain, is equal to propagation of one time period in the time domain. Understand? See, at every instant the real values matches with the instantaneous values of the time domain. The real value of the phasor quantity matches with the instantaneous value of the time domain quantity. Okay, now, so how this is rotating? It is rotating in anti-clockwise direction with omega radians per second. So one propagation of one time period in time domain is equals to rotation, one anti-clockwise rotation in the phasor domain of the same signal, So since it is a continuously rotating quantity, if you take the snapshot at a t equal to 0, that is nothing but the phasor diagram. Understand? So this is just for your understanding. So a phasor is a rotating polar quantity in the complex plane. It rotates in anti-clockwise direction with an angular velocity of omega radians per second. So a phasor is a rotating polar quantity. Polar numbers you might be aware in the mathematics. I'll just tell the difference between polar and phasor. A phasor is a rotating polar quantity in the complex plane. It rotates in anti-clockwise direction with an angular velocity of omega radians per second. The last important point is a phasor diagram is the screenshot taken of the rotating polar quantities at t equal to 0. A phasor diagram is nothing but the screenshot taken of the rotating polar quantities at t equal to 0. So these important concept you should keep in your mind. Okay. Now, how to convert from time domain to frequency domain? You already know, just we will take few examples. Let us say V1 of t is equals to 20 root 2 cos omega t plus 30 degrees. So many volt. This is a time domain signal. What will be the frequency domain signal? The frequency domain signal would be 20 root 2 at an angle 30 degrees. 30 degree, so many volt. We call this as V1. Usually small letters are denoted for time domain signals. Capital letters are used for denoting the phasor signals. Okay. Now, if you want RMS phasor quantity. So in order to get the RMS phasor quantity, what we have to do? We have to scale the amplitude by root 2. We have to divide the amplitude by root 2. So the RMS phasor quantity will become 20 at an angle 30 volt. This is RMS phasor. Okay. So in entire phasor diagrams in electrical engineering analysis, all the phasors you are drawing are RMS phasors only. Strictly remember this point. So knowingly or unknowingly in your phasor diagrams of transformer, induction motor, synchronous generators, all the quantities, all the currents, voltages and voltage drops, all are RMS quantities only. So all the phasors which you draw is the RMS phasors only. Okay. So from now onwards, we'll only write the RMS phasors. Next, suppose there is one current, say I1 of t. I1 of t is equals to 2 cos omega t minus 30 degrees, so many ampere. So its RMS phasor current would become how much? I1 is equals to root 2 at an angle minus 30, so many ampere. So many ampere. Okay. Now, the next important thing is the resistor in time domain. In phasor domain also it will be resistor in ohm. There won't be any change in the resistor when you transfer from time domain to frequency domain. Inductance in Henry will become, in frequency domain it will become SL. This I can write it as J omega L. S is equals to J omega. And the same thing I can write it as omega L at an angle 90 degrees. Omega L at an angle 90 degrees. Okay. So inductance in Henry will become SL J omega L, so many ohms. Okay. Inductance in Henry will become ohms in the frequency domain. Similarly, capacitor in farad will become 1 by SC in frequency domain, that is 1 by J omega C, that is minus J by omega C, or 1 by omega C at an angle minus 90. Again, its unit will become ohms. It will become ohm. Okay. So this is how we convert the resistor, inductor and the capacitor. Okay. So one more thing which I want to tell you is that whenever you write, say 2 Henry, then this quantity in, say L1 is equals to 2 Henry. When you convert this quantity into frequency domain, let us say our omega is equals to 100 pi. So how this value will become? This will become, people should not write x1 or xl1 is equals to j into 2 into omega, that is j2 omega so many ohm. This is wrong. This is wrong, because you should write this one as zl1 is equals to j into 2 into omega. Okay, this I can write it as j into xl1, j into XL1. So XL1, the inductive reactance is nothing but the magnitude, that is 2 times, that is omega L, or in this case it will become omega into 2, so many ohms. But you should never write XL1 is equals to J into something, which is an absurd, Understand? Reactance has no polarity. That means J will not come for the reactance. Either it is inductive reactance or capacitive reactance. XL1 means omega L1 only. Understand? So if you want to write it as complete reactance, you have to write it as ZL1 is equals to J into 2 omega, that is J into 2, J into XL1. Okay. Similarly for capacitor in farad, X is, let us write it as an example. C1 is equals to 2 farad. So your XC1 would become 1 by 2 omega, so many ohm. So your ZC1 will become minus J into XC1, that is equals to minus J divided by 2 omega, so many ohm. Okay, this is the correct notation. You should never write XC1 is equals to minus J by 2 omega, which is an absurd. Okay, this is how we convert the voltage signals, current signals, and passive elements from time domain to frequency domain. Understand? Any doubt in this concept, gentlemen? You might be aware of all these things, but some gaps may be there which I wanted to fill. Any doubts you can ask? Hello?
Yes, no doubts.
No doubts. Any other students? Any doubt you're having?
No, sir.
No, sir.
Okay. So now lastly, which I want to tell only one point. What is the difference between a polar and a phasor? Can anybody tell it? What is the difference between a polar quantity and a phasor quantity?
Polar is a fixed quantity, sir. Phasor is a rotating.
Good. Polar is a fixed complex number. Suppose if you have studied a complex numbers, suppose A is equals to 2 plus J3. It is a number. Understand? Similarly, Z is equals to say, yeah, 5 plus J 8.66 ohm. Now, how do we represent them in the complex plane? If I take a complex plane, then to represent A, my real value is how much? 2. Let us say this is 1, this is 2. Here it is 1, 2, and it is 3. Now, to represent A, my real axis term is this one, 2. My imaginary axis is this one. So, this will represent A. Where the real axis, real value is 2, imaginary value is 3. Understand? So this quantity is a polar quantity. Why? Because it is fixed quantity. It will not do any rotations. Understand? Even the impedance is a polar quantity, because impedance don't have the uh, rotational frequency. Understand? Whereas when I write the same thing as V is equals to 10 at an angle 30 volt, let us say, If I write it in the complex form, what I'm going to do, 10 cos 30 plus j or 10 sin 30. This value will become 8.66 plus j5. If I write the same thing, this value matches with z. 8.66 in this one. Let us say this is our this one. Now, what is the difference between these two quantities? A is a fixed quantity, polar. My voltage is a phasor quantity. Even though it appears fixed in the phasor diagram, but internally we should remember that it is continuously rotating in anti-clockwise direction with omega radians per second. That is the difference between a phasor and a polar quantity. Polar quantity is a fixed complex quantity, whereas a phasor is a rotating polar quantity which rotates in the anti-clockwise direction with omega radians per second. All this subconsciously an electrical engineer should know. Understand? So with this, the mathematical background that we require is over. Now, let us stop at this point. This analysis will take more time. Today we are having a session again at 3 o'clock. We'll continue, we'll enter into the RL circuit analysis, the concept of active power, reactive power, transmission, everything will enter into the actual power system analysis. Okay. So any doubt you can ask, otherwise you can leave the session. We will discuss the gate questions on the topic as and then that comes in the from the next class on next session onwards. We will be dealing with the gate questions. Okay. So any doubt, gentlemen?
No, sir.
No,
So
sir.
that's it for this session. We'll meet again at 3 o'clock. Thank you.
Thank you, sir.
Thank you, sir.